And for the second session, again, we have Professor Zain with us, and he'll be speaking on the title Features of Heterogeneous Catalytic Processes. So please, over to you.
Thank you very much. Thank you. Inshallah, Assalamu alaikum wa rahmatullahi wa barakatuh. Inshallah, this second lecture, I'll talk about heterogeneous features of heterogeneous catalysis. Of course, again, the title of our work is, or our proposal is, in situ design and the catalytic dynamics of nanomaterials for water and air quality monitoring and mitigation. Actually, to know about catalysis, we have to know classifications of catalysis. There are different types of catalysis. The main two types of catalysis are homogeneous catalysis and heterogeneous catalysis. Just a moment, I'll try to fix this monitor.
Yes.
No. Thank you very much. Classification of catalysis, it may be homogeneous catalysis or heterogeneous catalysis. We have to understand what's homogeneous and what's heterogeneous. Homogeneous means all the components in the system or in a reactor are or have the same phase. Means gas with gas, liquid with liquid, solid with solid, and this is very rare. The second is heterogeneous catalysis, means the components in the system are different phases, like gas with solid and or gas with liquid, etc. So in homogeneous means fluid, liquid or gas. Heterogeneous means mainly solid, because once you are talking about heterogeneous catalysis, then your mind will go to different phases. Yes, but it's mainly the catalyst will be solid catalyst. Okay. There are other types of catalysis we didn't mention here, like enzyme catalysis, which biological catalysis, using biological catalysis, and it is the most or the oldest type of catalysis ever. Okay, because it is the since creation of this world. We can say that catalysis has industrial chemistry, or the industry depends on chemistry, has more than 90% of this industry depends on the catalysis science. More than 90%. So catalysis is the main bone or backbone of industry, really. Because if I'll give you an example, which is, for example, sulfuric acid, preparation of sulfuric acid. It is very known and very famous and very common in industry. Another very important component which is prepared by catalysis as well, which is ammonia. I'll tell you the story of ammonia very soon, inshallah. Without ammonia, maybe most of us or many of the people in this earth would suffer of hunger because of the leak of ammonia. Just I'll tell you, inshallah, because it has many applications. As I just said, that more than 90% of industrial chemistry depend on catalysis, and more than 90% Of this 90% depend on heterogeneous catalysis. That means more than 80% will depend on of industrial chemistry as well depend on heterogeneous catalysis. So what's heterogeneous catalysis? We just mentioned that heterogeneous catalysis means different phases in the reactor. Different phases like reactants or product or the catalyst, all of these have different phases. Let's see. It has many features or many characteristics or many advantages. I'll just tell you recyclability, of course, safe to store, easy to handle, easy to separate from the reaction mixture, and they have long lifetime, avoid formation of inorganic salts, and easy and inexpensive. Also, it can be used in continuous or flow process. I'll just tell you something about the last item, which is they are continuous or flow process. We have two types in chemical reaction or reactor. It has two types. Either it's static or flow. Static means, do you remember when you were making a titration of HCl and NaCl, HCl and NaOH? This is static, means both are in the same reactor and nothing goes here or there. Or if it's under vacuum and you just add some gas on the solid, this is static. And there is another thing which is flow. Flow means some kind of liquid or gas just to go through the reaction and from one side and to go out of the other side. This is flow. This can be done in case of heterogeneous catalysis, but can't be done in homogeneous catalysis. Okay, let's have a quick comparison between homogeneous and heterogeneous catalysis. I'll tell you briefly what is the difference between them, or why we use heterogeneous catalysis, why industry favors heterogeneous catalysis. But let me tell you a brief story about homogeneous and heterogeneous catalysis. What's homogeneous catalysis? Homogeneous, do you know when you add some salt, NaCl in a cup of water, what will happen? You add a spoon of salt in a cup of water. What will happen? And you just stir it little. What will happen? All the salt will distribute all over the cup of water, right? And just listen, all the salt molecules will touch can touch all the H2O molecules, right? It will be in contact. Remind this in your mind, okay? This is first. Second is, this will cause rate of reaction will be higher rate of reaction because there is a contact between reactants, and if you feel H2O is the reactant and NaCl is the catalyst. So reactant H2O will be on touch with NaCl directly. So it will cause high speed of reaction, and selectivity will be high, and efficiency of the reaction as a whole will be high. Okay, so it's good. So you have to ask me. So if you feel it's good, why don't you use it in industry? Because if I want to tell you, please separate NaCl, which is the catalyst, out of the reactants. What will you happen? What will you do? Just try to evaporate and evaporate and evaporate water and evaporate until you find a piece of salt as a residue in the cup. Okay? This is a problem. This is the main problem of homogeneous catalysis. Although it has many advantages, but it has this problem, this main problem. This main problem makes people go to heterogeneous catalysis because even if it is less selective, less effective, less rate of reaction, but it will not cost me a lot to separate products out of the catalyst. Just if we use salt, for example, if we use, for example, sand, just add it in cup of water, what will happen? And reaction goes and something, everything is done. What will happen? Please separate it. Just filtration will be okay. But in case of sodium NaCl in water, separation will not solve the problem. Okay, so let's have a look to the advantages of homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis has the same phase. Homogeneous catalysis, catalyst separation is difficult, expensive, and difficult to recycle. It is difficult to separate and recycle again. Requires extensive purification steps, short life, and also difficult to handle. Because if I use liquids all the time, it is difficult to handle. But if I use solids sometimes, it is easy to handle. But the green color, but it has high selectivity and the high catalytic activity, low reaction temperature. It is better in these 2 items or 3 items, but it is bad in the problem is purification or separation. In case of heterogeneous catalysis, different phases, easy to separate catalyst or the product from the reaction. Easy to separate, and this is the main advantage of heterogeneous catalysis. Easy modification of the catalyst, readily regenerated and recycled, long life and less purification step, but it has low selectivity, high reaction temperature, relatively difficult of modification of the catalyst. Also, heterogeneous catalysis has a good advantage over homogeneous catalysis. For example, if you use homogeneous catalysis, water as a solvent, what is the maximum temperature you can go in this reaction? The maximum temperature is the boiling point of water. But in case of, if you use heterogeneous catalysis, you can see this material may go to 100 degrees or 200 degrees or to 500 degrees or even 1000 degrees. Whenever it can go with you, it will be okay. But in case of using homogeneous catalysis, the boiling point of solvent is controlling you. These are some examples about the heterogeneous reactions. In case of using catalyst as a liquid and reactants are the gas, like polymerization of alkane catalyzed by phosphoric acid. And this is catalyst and reactant, solid and liquid, like decomposition of hydrogen peroxide. And this is very famous reaction. The other one is if you use catalyst as solid and reactants in gas phase, like ammonia synthesis. Ammonia synthesis is one of the most important reactions, in ever known ever in chemistry. Okay. The other one is if we use catalyst as solid and reactants is solid and gas, like hydrogenation of nitrobenzene to aniline catalyzed by palladium. These are some examples of the heterogeneous catalysis. Now, let's have a look about the advantage of using heterogeneous catalysis, like this reaction. Of course, in air, we have oxygen, hydrogen, nitrogen, and etc. If you have oxygen and the nitrogen, oxygen and the hydrogen together in the same bottle or in the same tube, of course they may remain for 1 year or 100 years together without reaction. You have to have very high temperature for them to react, to colloid and react. We just mentioned in previous lecture that to have effective collision, you have to have a reaction, you have to have collisions, and these collisions should be successful and should be have two factors, which are orientation and energy. Here we have to make cleavage of OO bond, which is double bond, and make cleavage of HH bond, which is single bond. These need high energy to do. In gas phase, this reaction is very slow. Even if it is thermodynamically favorable, but it will not happen. Okay. On as you can see, delta G of this reaction is this amount because it needs energy to cleave the bonds of double bond of oxygen and single bond of hydrogen, and other energy to react and so on. So what is the solution for this reaction? If you have a piece of platinum, you add only a rod of platinum in this tube that we are talking about. It has oxygen and hydrogen together. If you add only a piece of platinum, a rod of platinum, you will notice drops of water on platinum, even at room temperature. Why? Because of heterogeneous catalysis. That happened in this for this reaction. Absorption of platinum, absorption of hydrogen over platinum will cause cleavage, cleavage of HH bond, and the absorption of oxygen over platinum will cause cleavage of OO bond with nearly activation energy equals nearly zero. Nearly zero means very low. It doesn't mean zero. Okay? It's like this. If this is oxygen, and hydrogen, and cleavage occurs, and then water is formed, and water leaves the surface, and so on. In this case, it is a very fast reaction. At room temperature, it may happen with nearly zero activation energy. The other example is nitrogen with hydrogen to form ammonia. But briefly, I want to tell you about ammonia. Ammonia is the most important, nearly the most important product ever have been done by heterogeneous catalysis. Why? Because in early ages, they tried to find an alternative for organic or natural fertilizers. Because if we only depend on natural fertilizers, I think there is no food will be enough for the population in this world. Okay, before the war and before the need of this high amount of food, it was nearly okay. But Le Chatelier, by the end of 18 approximately 1890, 1890, 1895 in this time, tried to prepare ammonia from this reaction. But first, he tried to prepare ammonia from the reaction N2 plus H2 will give NH3. And he tried, and he succeeded to prepare ammonia. But the problem is to establish or to construct a suitable reactor for this reaction. Because this reaction is tough. This reaction is very hard. This reaction needs high pressure. It needs high temperature to make cleavage of N3N and HH. It needs high temperature, high pressure, and so it needs a special reactor. At this time, he tried, and he was nearly almost succeed. And in the final step of his experiment and his design, he just exploded, and one of his team died. So he quit, just said, I'll not play again in this game. And he already quit this reaction at all. After only 2 years, Haber and Bosch, those are German engineers, came and tried to establish or build this reactor, and already, alhamdulillah, succeeded to build this reactor, and they got a Nobel Prize, I think, in 1918. This last century, maybe 100 years before, because of the importance of the preparation of NH3. NH3 used is maybe it is used in 85% of its preparation is used in fertilizers, and these are some types of fertilizers prepared from ammonia, and this is ammonia uses 85% of ammonia, and this is the reaction. Ammonia N2 plus H2 gives NH3. This is exothermic reaction. It is like this exothermic reaction. it needs high energy to make cleavage of N3N and 3 H2 to gives 2 moles of NH3. Okay, and some energy to complete the reaction. This is a complete system of ammonia synthesis, but I will only focus on the reactor. In this reactor, this is a compressor. This one is a compressor, and N2 hydrogen mixture with 1, 2, 3 is going through this compressor. It goes to the surface of the catalyst, which is iron catalyst, and the cleavage of these molecules occurs on this catalyst to give NH3. Then we have a mixture of NH3 plus nitrogen and hydrogen, which didn't react in this reaction. These are the mixture we have. It goes to NH3 here, and this is a cooler. Water comes goes in these tubes as a cooler, and nitrogen and hydrogen are almost permanent gases. They go to again to the system and start and make the reaction again. And the nitrogen and the NH3 will be separated from this step, as you can see here. This is a system to prepare ammonia. But for this system, what do you think? Will we need very high temperature, or will we need very high pressure, or what? I think in this mixture, of course, you know that for exothermic reaction, we consider high heat as a product in this reaction. For this exothermic reaction, what do you think? To just heat the reaction to produce ammonia more, or cool the reaction to produce ammonia more, or more ammonia? To cool the reaction. Okay, we should cool the reaction. It's very nice to cool the reaction. Either it works at 500 degrees, so let's go to 400 degrees, it will be better. Let's go to 300 degrees, it will be very good. Let's go to 200 degrees. It doesn't work. What is the problem? Because we need to decrease temperature, yes, but for limited level that maintain enough energy to make collisions to proceed the reaction. Let's see. This is, for example, I wanted to show you how is equilibrium. For equilibrium, of course, you know equilibrium: A plus B equals C plus D, and heat will come as a product. Okay, and this is equilibrium. So Le Chatelier, I'd like to remind you with Le Chatelier principle. If you have an equilibrium, a reaction at equilibrium like A plus B equals C plus D, and plus or minus heat. This means if you affect this reaction with any external effect, it will oppose the effect you did. This is simply Le Chatelier principle. If you affect it, if you make external effect on the reaction, it will oppose or will try to oppose your effect by decreasing it. Like if it gives you heat, then if you give it more heat, then it will go to backward reaction, or vice versa. If you give it A, it will go to C plus D. If you supply it with C or D, it will return back to A plus B, and so on. This is Le Chatelier that we were talking about Le Chatelier. And by the way, he, after the problem of ammonia, he published an article later, and he just said that he made a mistake to leave this problem, and he denied or regret to leave ammonia synthesis slipped from his hand. He published a paper after 5 years from maybe 1905. Anyway, here heat is considered as reactant like concentration, reactants and products, and something like this. Okay. In this reaction, H2 plus nitrogen equals NH3 plus some heat. In this exothermic reaction, by Le Chatelier principle, as your friend just said, that if we affect this reaction by adding temperature, of course, it will go in the reverse direction. But if we just cool it, it will go to forward direction. And this is simple thermo. This is each one of them. The amount of ammonia with temperature at different pressures, at 1 atmosphere, 3 atmosphere, until 300 atmosphere. We keep pressure constant, but we change the temperature. Of course, if we change the temperature, this means, as you can see here, that from higher temperature to lower temperature, as you can see, at 500 degree, the amount of ammonia was very high. If we keep at 300 atmosphere, the amount of ammonia was very high. And if we increase temperature, the amount of ammonia decrease. If we take any other one at 10 atmosphere, the amount of ammonia decreases with increasing the temperature. If we establish the temperature at constant temperature, for example, at this temperature, if we go up at different pressures, what will happen? Increasing the pressure leads to increasing the amount of ammonia comes here. Because as you can see, you can 1.5 mole of hydrogen plus 0.5 mole of nitrogen to give 1 mole of NH3. This means pressure decrease in this reaction. Means if we increase the pressure, it will lead to decreasing the pressure and the reaction will go forward. Okay, I think it is understood. And this is another story of decreasing the temperature at different pressures like this. As you can see, if we keep the pressure at 200 by increasing the temperature, the amount of ammonia decrease. And here is by decreasing the temperature, the amount of ammonia increase. This is ammonia, and you can see the best catalyst used for ammonia preparation is from transition metals, which is in this order. Why they are using? Because they are sometimes we use better catalysts like lithium-containing catalysts, but these are not good because they are too stable. Too stable means they are stable. The product is stable more than enough. This means the cycle will not continue. It will be interrupted. The cycle will be interrupted. Okay. And these are some examples of the preparation of ammonia. In using the iron is the best because it gives from 60 to 70% efficiency at when is mixed with alumina and the calcium and the magnesium. I think we had a good idea about ammonia since it is the most important reaction in heterogeneous catalysis. In this case, this is, I think, it says what we already discussed before that. We need to decrease temperature, but we should keep it in the range of 250 to 400 because we need this energy to make collisions and complete the reaction. Because we can't only decrease the temperature to room temperature. At this time, there is no reaction will occur because we need some energy to make collision and to overcome activation energy. The role of catalyst. This is the role of catalyst that it makes heterogeneous catalysis. It makes absorption of hydrogen and of nitrogen together very close to each other to have a chance to colloid, to have a chance to react. It's like if you have your friend, either you can discuss with anybody, just to go to some place like restaurant or like cafe or something, just to take a table and two chairs and sit and discuss. It is the same. Like nitrogen goes to active site, just beside hydrogen in the beside active site, and they are very close to colloid and they interact together and they give NH3. Now we will have another example of heterogeneous catalysis of heterogeneous reaction, which is N-hexane reaction over the platinum and in presence of hydrogen at very high temperature from 500 to 700 degrees C. Now I'll tell you what will happen, and I will have a question after my explanation. Here in this reaction, it may make aromatization. It may make cyclization to give aromatization to give benzene, cyclization to give methyl cyclobentene. And it may make isomerization. Another possibility, it may make hydrogenation to give propane. This reaction, of course, we just add N-hexane and add platinum as a catalyst and just flow hydrogen at high temperature. In this reaction, what do you think? Does it have good selectivity or bad selectivity? If you understand what I have just said in previous lecture. Bad selectivity. Why does it have bad selectivity? Because no, because it have several products. We don't know how much it is, and we will have so much time and the effort to separate these reactions. On the other hand, if we check this catalyst in syngas is a mixture of CO plus hydrogen, synthesis gas. Okay, in syngas, for example, if we add syngas together in presence of copper, all of these are heterogeneous catalysis as well. It will give us formaldehyde. However, if we add the same mixture in presence of other catalysts like nickel, of course, it will give CH4. Another story, if we have iron and cobalt together, it will give alkane. There is another possibility, if we have copper with zinc, chromium, it will give methanol. A fourth or fifth possibility, rhodium cluster, it will give glycol. What do you think about selectivity in this reaction? I think selectivity is is perfect because it's a key. If you want to have alkane, just to go to iron and coke. If you need methane, just to go to nickel. If you need, for example, methanol, just to go to this mixture of oxides. Okay, this means it is good selective, has high selectivity, and all of these are heterogeneous catalysis. This means you can see all of these are sources of power, sources of energy, all of these sources of very important chemicals, all of these are becoming, or all of these are obtained from heterogeneous catalysis. Let's go to, okay, thank you very much. I think it's a short lecture, and I am happy to finish it. Thank you very much.
Is there any question from the audience? You can ask anything.
Okay. Thanks, Professor Zain, for the valuable lecture. I hope the lecture is beneficial for you all. And if you have any queries, any discussion, please discuss. Okay. Thank you very much.
I told you once you don't have